Kanyini is South Australia's first CubeSat, scheduled for a 3-year research mission. It carries a hyperspectral payload, cosines HyperScout-2. The spacecraft's limited available power restricts image capture, onboard processing as well as data downlink. Our research team, with experts from the University of South Australia, Swinburne University and Geoscience Australia, has developed, as part of a SmartSat CRC funded project, an energy-efficient solution for onboard early fire smoke detection. Our team will present in the following: a machine learning model and onboard processing concepts demonstrated on a simulated fire event. Traditionally, AI-based fire smoke detection using multispectral or hyperspectral satellite imagery is conducted on ground. However, CubeSats do not have the capacity to transfer large hyperspectral datasets to a ground station. Processing hyperspectral imagery on board using lightweight AI models would solve the downlink constraints. Only application-specific results, such as fire smoke locations, would need to be downlinked. This would also be crucial for providing timely information to early warning systems. The highlights of our research include a lightweight AI model and energy-efficient onboard imagery processing for early fire smoke detection. Our onboard AI approach clearly outperforms the AI on-ground alternative. Our demonstration shows that AI onboard reduces the data downlink volume to 16% of its original size while consuming 69% less energy. In addition, AI onboard detects fire smoke 500 times faster. Thinking ahead towards a CubeSat constellation, our approach opens up further research opportunities towards smart communication and early detection. The following slides will provide further technical details using a demonstration example. To demonstrate the AI model, we have used a simulated Kanyini image over a past fire event in South Australia. The input hyperspectral image has 45 spectral bands, at 75 megapixel resolution. A smoke plume and cloud are clearly visible in this natural color image. Various false color composites, including new ones derived in this project, help to highlight the presence of burn scars and vegetation and separate out the smoke, cloud and aerosols from the background land cover. The AI model will use its training smoke and cloud signatures to detect the presence of smoke in this image. The AI model is developed and trained on ground before uplinked to the satellite. To detect fire smoke on board, the acquired imagery is first partitioned into tiles, using relevant selected bands. These tiles are then fed into the AI model. Only the tiles that contain smoke are merged and downlinked to the ground. Downlinking only the segments that contain smoke can greatly enhance downlink transfer efficiency, which is crucial for the early fire smoke detection application. In our example of the fire event in the Coorong, only 11% of the tiles contained smoke. Compared to the traditional scenario, that is without AI on board, our approach resulted in an estimated 62% reduction of the satellite's power consumption for both onboard processing and downlinking of hyperspectral imagery. We developed a convolutional neural network model that comprises of spatial and channel attention together with other neural network layers. The input to this model include multispectral satellite imagery bands. The output of the model is the prediction of whether an image contains smoke. This model is small, accurate, and fast and has been tested in our simulation hardware. The HyperScout-2 sensor was emulated using VIIR's satellite data, with band gaps filled through spectral averaging and adding statistical random noise. Information was then super-resolved to the Kanyini HyperScout-2 pixel size. New algorithms were developed for the automated detection and masking of smoke and cloud to produce the training dataset tiles, using just 5 wavelengths. We used a risk-adverse approach for smoke detection with removing pixels that were highly unlikely to be smoke or cloud. This reduces the chance of missing detecting a smoke pixel when it is present. To evaluate the performance of our AI onboard fire smoke detection approach, we developed an emulation system using a Raspberry Pi and Intel Neural Compute stick that closely matched the specifications of the Kanyini satellite system. Our emulation system measures the running time, average memory, peak memory, and power consumption of each onboard processing step. In our demonstration example, the acquired emulated Kanyini imagery has dimensions of 3072 by 1856 pixels with 45 bands in the visual and near-infrared spectrum, resulting in a file size of 489 megabyte. The tiling and band extraction step produces 84 tiles, each with a dimension of 256 by 256 pixels and 3 selected bands, resulting in a tile size of 0.38 megabyte. Applying the AI model inference, 10 tiles containing smoke are detected, which are then merged back into an imagery with identical dimensions, bands, and georeferencing information as the original imagery. The merged imagery is compressed from 489 megabyte to 61 megabyte and split into 122 small files for downlinking, each with a size of 512 kilobyte. Among all steps, compression is the most time and power-consuming operation. In summary, our AI onboard processing approach consumed 0.142 watt-hours of power and produced 122 files for downlinking. In contrast, without AI on board, the power consumption for onboard processing is 0.117 watt-hours, but with 778 files for downlinking. Data transfer is simulated using a developed framework, as testing on the actual satellite unit is currently unavailable. The framework does model and render the geolocation of the satellite at a given time, or frame. Distance between the satellite and the ground is calculated. A packet of data is considered transferred within the communication range. The satellite position is then updated to the next frame, and this process repeats until the entire file is completely sent. Different combinations of file size and transfer speed are performed to indicate the time required in these scenarios. For our demonstration example using a fire event in the Coorong, the total data transfer time between simulated image capture and completed downlink to the South Pole ground station added up to 31 minutes. To conclude, our collaborative research team is providing a solution for energy-efficient, AI-based onboard processing of hyperspectral imagery to support the automated early detection of fire smoke for Australian bushfires. We have developed a large fire smoke training dataset of labeled hyperspectral satellite imagery, a lightweight AI model for fire smoke detection, and a pipeline allowing developed models to be assembled with the onboard processor and AI unit. In addition, we have conducted a power performance analysis of the emulated onboard processing steps, as well as a data transfer analysis. Our research highlights significant benefits of onboard AI compared to traditional on-ground processing and could be applied to multispectral or hyperspectral CubeSat sensors and applied to various applications, including early warning systems for disaster risk reduction.